Coming over here, we discussed about some asymptotic notations in the last class. Also, we discussed this big O notation, omega notation, and theta notation. One second, I'm starting video recording.
This meeting is being recorded.
Okay. And as we discussed about all this mathematical representation, today our topic is we already completed notation, omega. Okay, right now coming for the amortized analysis. This analysis, it is a technique which is used in computer science. To analyze the average base time complexity. We already discussed about base time complexity, average time complexity, and of course least time complexity, worst time complexity. Here, this analysis will be done only for average to calculate average time complexity of algorithms, which will perform sequence of operations, where some operations may be more expensive. But of course, the product cost of these expensive operations will be such multiple operations, so that average cost of each operation is constant. Of course, sometime low. This analysis will help for us to create, while creating the algorithms, occasional operations is very slow generally, but most of other operations are faster. And in this analysis, we analyze a sequence of operations which will guarantee what will be the worst average time, which will also help us to particular. Second, we are highlighting. Okay. And the time is particularly expensive operation. The data structures whose operations are analyzed using Amata. This analysis also includes hash tables, which you people already learned in data structures, as our unit 1 is completely about 1 second. And data structures, here we will discuss about data structures also. That is hash tables, disjointures, and split trees. These are the different types of data structures. These three different types of data structures will be used in this analysis, amortized analysis. Okay. And coming for the hash tables, how the hash table works. We already know why hash tables are used in the data structures and what is its purpose. Generally, here hashing refers it's nothing but a process which will generate fixed size output from an input variable using such as mathematical functions which are already used in hash functions. This technique determines an index or location for the storage of an item in the data structure. Simply, we will follow what is the index point we are using and at what location the storage has to be stored and how this data will be accessed from the memory. Everything will be comes under a function called hashing, and for that purpose we use hash tables. It comes under data structures. And coming for the disjoint sets, these are the sets whenever you are using any common element, which will be intersected results. I mean, by combining any two elements, there may be the point, intersection point, which will show as empty set or null set. We can call such sets as disjoint sets. These are mutually exclusive sets or independent sets. Why we are calling it as mutually exclusive sets is because whenever a common value is shared between two nodes or two elements, these two elements has to comes under one deeper understanding, saying that in one way direction you will send the data and in another direction you can receive the data. Such sending and receiving in the memory at different locations will be possible by using these sets. That's why we are calling it as independent sets also. And if you take a formula, for example, if P equals to AB and P equals to CD, if you make an intersection, that is P intersection Q, equals to, of course, here we are taking a value as theta, as there is no same element in the set P. Why? Because if you people know this unions, intersections, right? Union means whatever the values are there in both the sets, both are combined. Whereas in coming for the intersection, any common point will be noted. I mean, in Venn diagrams, you see all these things. So here the P value is AB and Q value is CD. Is there any common point? For example, if P is ABC and Q is CD, then intersection point will be the C. As there is nothing, we can call it as null point. Thus P and Q are called disjoints. Why? Because even though there is no common value, we want to intersect both the things. And here the value will be the null point. And coming for the split trees, it is a self-adjusting binary search tree. It also comes under data structure, which means that the tree structure is adjusted dynamically based on the accessed or inserted elements. whenever any n number of elements are going to insert dynamically, so we can insert dynamically by using this place this. Of course, it is also a type of binary search tree where the data will be found by using the same methodology. In other words, sure. In other words, the tree automatically reorganizes itself so that the frequently accessed or inserted elements become closer to the root node. Why? Why? Because whatever the node we are adding keep on, this plate tree will always take that node to the root. And coming for the applications, this analysis is useful for designing efficient algorithms for data structures such as dynamic arrays, where the array size can be uh, resized dynamically, priority queues, and where the queue structure is nothing but kilo structures. FIFO structure, first in, first out. In the structure, if there is any priority for any queues which we are going to intercept, we will use such priority queues. And disjoint or set data structures. As now we discussed the design sets are those whenever you are using the intersection points between where there is no common value, we can call them as disjoint sets. In such applications, we will use. And it will also ensure that what is the average case time complexity if the operation remains constant, even if some operations are expensive. Of course, sometimes it may cost more, but the thing is we need what is the time complexity, average time complexity. If we don't know such average case time complexity, we cannot predict and we cannot write the algorithm. Of course, with the help of the data structures only, we can create the algorithm. While creating the algorithm, we must follow the data structures. Why? Because data has to be stored in the memory, right? Instead of analyzing the worst case time complexity of an algorithm, amortized analysis considers the cost of multiple operations performed over time, which gives an upper bound on the running time for the single operation. Okay. And here, if you see the figure with the help of the hash table insertion, here the table size is dynamic. When we design an hash table, which must be decided by the table size, of course, there is a trade-off between space and space and time. There is always analysis between, once again, there is always a trade-off between space and time. If the hash table size is large, such time becomes slow. Why? Why? Because if the as table is big, the number of elements which were inserted will take some time to search wherever our actual value is there. But the space required will be increased. Why? Because more number of elements wants to store, more number of table cells will store more number of elements. As we are discussing about the dynamic table, here whenever we insert one item, it will occupy only one memory space. That is nothing but one cell. Second one, second, third one, again it will take two. Why? Because earlier it was two, so it will take two. It will occupy two values. So it will assume that you will wants to insert two more elements. That's why by default, when you inserted first element, it has inserted. Why? Because without any extra space. Why? Because earlier the value was null. Whenever you are inserting second point, I mean second value, as the first value is already existed, it will give the space dynamically for the second value. And whenever if you want to insert third item, earlier there are two values which are already occupied by the two memory cells. So by default, it will think that you wants to insert one more element. So that's why whenever if you want to insert the fourth element, whether you inserted or not, the space will be provided when you insert the third element. In such a way, if you want to insert fifth element, again it will think that how many values are inserted earlier? One, two, three, four. So by default, whenever in the hash table, if you want to insert one more element other than this four, by default, it will think that, okay, the fellow wants to insert three more elements and it will provide three empty spaces to insert new values. In such a way, these three empty cells can be occupied by three different values like 6, 7, 8, and so on. And after completion of 8, if you want to insert the ninth element, depending upon the register size, it will help whether to provide. Of course, the register size, if we take 8-bit register, as there is no space, it will not ask. If you are using 16-bit register, if you want to insert ninth element, again 8 empty spaces will be created. Next overflow would happen when we insert the 9. Insert 9, table size will become 16 if you are using 16-bit registers. The solution to this trade-off problem is to use dynamic array. The idea is to increase the size of the table wherever it becomes full. Following are the steps to follow when the table becomes full. For example, allocate a memory for larger table size, typically twice the whole table. Whatever the whole table exists, you must insert, you must allocate, you must provide. exactly double to the older table. So then we can copy these contents old table to the new table where free the old table so that the old table will be free. If the table has space, which is simply insert a new item in the available space, the worst case cost of n inserts equals to n into big O n, which is O to the power O into the n square. This analysis gives an upper bound, but not a tight upper bound for n insertions, as all insertions don't take 3 time. Okay. If you take the formula, if you go for the representation for item number 1, 2, 3, 4, one second, yes, this one. Hmm. For item number 1, 2, 3, 4, the table size 4 is enough, whatever the value wants to insert. If you want to insert first item, the table size will be 1. If you want to insert second item, the table size will be 2. If you want to insert the third item, the table size will be 4, where another space will be provided to enter the fourth element. In the same way, if you want to insert the fifth element, it will provide new 4 spaces. Why? Because earlier old table contains 4 values. It will provide 4 memory spaces dynamically. So whether you are inserting fifth element or sixth element or seventh element or eighth element, it will provide a space with four different spaces to insert 4 different values. And whenever if you want to insert ninth element, by default, as the old table contains 8 values, it will create 8 empty spaces where the address starts from 9 to 16. So that's why the last address of the cell is 16. You can insert the ninth value in the ninth position, 10th value in the 10th position, where the memory size is 16 bits. Okay. So if you come for the cast, how many values you are entering, depending upon that cost will be varied. For example, for the first element, first total table size, it will take 1. For the second element, as a second element, the cost will be around 2. For the third element, even though it is providing 2 spaces, even though it is providing 2 spaces, 4 spaces, 3 and 4, you insert the value 3. So the cost will be the element cost only 1, 2, 3. And here it ends. And whenever you are inserting the fourth element, you are not creating separate memory space. The memory space was created earlier whenever you created third element. So that's why the cost will happen only, the effective cost will be the cost of this fourth element. The fourth element is the first element without creating any other space. That's why its cost is 5. Okay. And if you come for the fifth element, what will happen is actually you are inserting fifth element. It is going to create 4 spaces, but you entered only one element and the element cost will be the 5. If you want to insert the sixth element, the cost will be 1 again. Why? Because space is already created. Whenever you are coming for the fifth, it is the new table. It is the it is the new table where this new table with old number 5, item number 5 is inserting, the cost will be the 5. And whenever this was created, automatically 6, 7, 8 spaces were created dynamically. So for these 3 things, whatever the element you are inserting, that element cost will be the effective cost. So for sixth element 1, for seventh element 1, for eighth element 1. And again coming for the ninth element, ninth element will cost around 9. Why? Because already 8 elements were inserted, and wherever you are creating the new dynamic table, that will cost the cost of that value will be the cost of the item number. Okay. In such a way, 16, 10, 11, from 9 onwards, 10, 11, 12, 13, 14, 15, 16, each and everything will cost 1. So here amortized here system here amortized cost will be the cost of 1 plus 2 plus 3 plus 5 plus 1 plus 9 plus 1 and so on divided by n. Whatever the element cost, effective cost we are taking here, we will add all these things and divided by n. N is the number of elements. We can simplify the above series by breaking terms 2 into 3, 2.3.5.9 into 2 sets, 1 plus 1 plus 1 into another set, so that we can make an logarithmic formula. Amortized cost equals to square bracket, 1 plus 1 plus 1 as the n number of items, 1 plus 2 plus 4 and so on as a log to the log n minus 1 to the base 2 plus 1 n terms divided by number of elements, that is n. In simple, n plus 2n by n. Here, depending upon the n value, the output will be less than or equals to 3. Amortized cost equals to big O of 1. Okay. In such a way, amortized cost is the cost of the element which was inserted depending upon the array size. I mean table size. So using amortized analysis, we could prove that dynamic table scheme has big O of n insertion time, which is a great result used in hashing. So next we are coming for the basic data structures. The data structures which you are studying from BTech onwards. So same thing here also. We will just define whatever the data structures we are going to. Just we will reveal whatever the data structures we learned in undergraduation. So coming here, the basic data structures are classification of data structure. If you see the classification, data structures are classified into two types. One is you people better know linear data structures, and another one is non-linear data structures. Linear data structures are those which contain static structure and dynamic data structure. And non-linear data structures are the best examples are tree and graph. And coming for the linear, array, queue, stack, linked list, all these are linear data structures. Why? Because the in these data structures the data will be stored linearly, and each and every node will contain the next node, next values, address, and everything. And coming for the tree and graph, this is non-linear. Depending upon the tree structure in the graph or tree, we can point out one node to with another. So in general, data structures are the fundamental building blocks, right, of a computer programming. They define how data has to be organized and how the data will be stored, and how it will be manipulated within the program. Understanding this data structure is very important for developing effective and efficient algorithms. Algorithms can be developed only with the help of these data structures. Why? Because data structure will say, I mean, whether it is linear or non-linear, what type of data structure you are using, depending on that, where the element was stored and how the element has to be carried forward through logic gates. How these logic gates will help, whether it may be the insertion point. Why? Because in the insertion point will help us what is the average case, average worst time to be calculated while transferring the data. So these data structures will help to create an algorithm depending upon its type. So linear data structures where elements are arranged sequentially or linearly, where each element is attached to its previous and next adjacent element. Why? Because it contains three parts. Is called a linear data structure. The best example for that one is array, stock, queue, linked list, etc. Array, even in array, it will say what is the next value and what is the present value. Stack will say with the help of push and pop, and queue will say with the help of enqueue and dequeue operations. Linked list will always say how can we link one node with another node with the help of the address, etc. So coming for the static data structures, it has a fixed memory size. It is easier to access elements in the static data structure. Best example is array. Why? Because in array the size is fixed. Okay. And coming for the dynamic data structure, we can take example as stack or queue, etc. But in dynamic data structure, the size is not fixed. Why? Because the name itself is saying that it is dynamic. It can be randomly updated during the runtime, which may be considered efficient concerning the memory space complexity of the code. So it will also check how the code has to be executed with the help of the memory space. If the memory space is too far, it may take some more time to execute the data so that it will arrange the data in a structure. And coming for the non-linear data structures, these are the elements where the elements are not placed sequentially or not linearly. That's why we are calling it as non-linear data structures. Here we can't traverse all the elements in a single run. Best example, trees and graphs. Here in linear, we can traverse where actual node is there. But coming for the trees and graphs, if you take tree as an example, where it contains again root node, leaf node, and to traverse, there are different traversing methods are there to find out where the element is present. Next, coming for stacks and queues. A stack is a container where the objects will be inserted in the LIFO structure, I mean LIFO principle, last in, first out. In the push down stacks, only two operations are allowed. One is push operation into the stack, and another one is pop operation from the stack. A stack is a limited access data structure element which can be added and removed from the stack only at the top. Why? Because as why? Because Why? Because stack is nothing but it will like a container, and where this container can contain either push operation or pop operation. Where push operation will add the item into the stack, pop operation will remove the item from the stack. And of course, a stack is a recursive data structure. We can use how many times we want. But only top element can be removed. Only we can insert the element on the top of the stack. Best example is the simplest application of the stack is reverse a word. You push a given word letter by letter and then pop letters from stack. For example, another application is like in MS Word or whether it is a PowerPoint or a Word, anything it may be, we use undo operation, right? In the text editor. These operations are accomplished by keeping all text changes in stack. Means you can do undo operation, redo operation only with the help of stack only. And coming for the implementation, if you take standard library of classes, the data type stack is an adapter class, meaning the stack is built on the top of other data structures where the underlying structure for a stack could be an array or a vector or array list or a linked list. Of course, in any other correction it may be. Regardless of the type of this underlying data structure, a stack must be implement the same functionality to insert on the top and to remove from the top. This is achieved only by providing unique interface. For example, to create such unique interface, we are having some syntax. And this is the syntax: public interface, stack interface of any type, means whether it is array, list, or array anything. Public void push from the top. Public any type of pop, whatever the type you are using, whatever the type of data structure you are using, you can use push operation, and you can use pop operation, and of course you can use peak operation. Once if there is it is empty, you can add a boolean expression as empty, yes or no. And next, coming for the queue. A queue is a container it is also a container, but it is an object where it contains the operations in a FIFO principle, FIFO structure, first in, first out, means that are inserted and removed according to the first in, first out principle only. Excellent example for this one is mm, like line of students in the food court of UC, means new additions to a line made to the back of the queue while removal happens in front after serving the food. In the queue, only two operations are allowed. One is NQ operation, other one is DQ operation. NQ means to insert an item into the back of the queue. DQ means removing the front item. The difference between stack and queue is removing. Why? Because who enters last will be removed first in the stack. Who enters last will be removed last in the queue. In a stack, we remove the item most recently added, whereas in a queue, we remove the item least recently added. That is the only difference. And coming for the, I mean, main difference, basic difference. Coming for the implementation, same here also, we will use an interface where our interface will help in such a kind. Uh, it is also, we will use this queue also an adapter class, means the queue is built on the top of the data structure only. Underlying these data structures, the underlying data structure for a queue could be an array, it may be a vector, or it may be an array list, or it may be a linked list of any other collection. Of course, regardless of this type of underlying data structure, a queue must be implement the same functionality. This is achieved by providing unique interface. The unique interface is same, but here whether it is empty or not has to be decided first. That's why in the queue interface, we will take public boolean is empty as the first instruction, and then only which type of element has to be inserted, it will be inserted at the front. That is NQ operation with a function called get friend. And to remove, we will use the DQ operation. And of course, public void NQ. The people will be DQ'd from the front. Means in the Boolean operation, we will check whether the condition, whether the queue is empty or not. If it is not empty, we will go to the front. Then we will do the DQ operation where the space has to be provided, right? At the front, we will perform DQ operation. Then at the back, the space will be provided to enqueue the data element. In such a way, we will use enqueue operation at the last, and finally clear function. And next, coming for the list. List is a data structures which resembles an array. It contains number of elements which are one after another in certain order. For example, 3725 is our list of it. Let us think it is a list of 4 elements, and we want to implement the list in such a manner that we can access the element in the last based on the index. And we want to able to add the, of course, add and also remove the elements. For example, there are two different types of lists are there. One is array list and one is linked list. Array list is purely based on an array where the information is stored in an array. We know what actual array data structure will help us. Since data item, since all the elements in array list are stored after one another in the memory, we can access any information from the list. The challenge is that the array is of fixed capacity, and if you want to change the capacity, we have to reserve a new array and copy the content into that. Whereas in linked list comprises of nodes. Why? Because which each contain one element of the list. A linked list can be linked to one direction and both direction. That is, it may be a single linked list or double linked list. In a single linked list, each node has a reference to the next node, and in double linked list, a node has a reference to the both of the next and previous one. That's why in the only the difference is that in the single linked list it may contain a connection with the single node. In double linked list it for previous and next one. So if you see the figure, it will look like this. A linked list is a fundamental data structure generally in our computer science. It also allows insertion and deletion in very easy manner where easily identified and can understood. A single linked list is a fundamental data structure. A single linked list is a fundamental data structure which contains nodes where each node contains data field and a reference to the next node in a linked list. The next of the node is null, indicating the end of the list. Whenever if you see the node is containing empty, if you want to end up this linked list, the final node will always contain null space. Whenever if the second part, if the each data field and reference to the next node. Whenever this reference field is empty, this data field and this is reference field. This reference field always says which node has to be linked. For example, it contains B's address and B reference field will contain C's address. C reference field will contain D address, and D reference is null, saying that linked list is over. So every time each and every node in single linked list, every time each and every node, as it contains two fields, one is data field, another one is reference field, next node address and previous node address. In single linked list, every node will contains next node address. But in double linked list, it contains next node address and previous node address. So that true and false. A double linked list is more complex data structure when you compare with the single linked list. Of course, there are some advantages also. It allows for efficient traversal of the list in both the direction because each node contains a pointer to the previous node and a pointer to the next node, where it allows quick and easy insertion and deletion of nodes into the list. From the list, as well as efficient traversal of list in both the direction. So if you take this head one, okay. uh, If we take this head node, initially null. As we are starting from here, the first node contains three parts. One is data field, another one is reference field, next reference field, and another one is previous reference field. So if you take data, you take node 2, it contains data field, next reference address, which node has to be connected, that address will be here. With the help of the pointer, we can find out that node and previous reference field where it contains previous address of the data. In such a way, it will also, the double linked list also end with a null reference next reference field. Okay. If the next reference field is null, it can come to the understand, it can understand that here it is going to be and the double linked list. Next, coming for the circular linked list. A circle linked list is a special type of linked list where all the nodes are connected to form a circle. Unlike regular linked list, which ends with a node pointing to the null. So the last node is a circular linked list, points back to the first node. This means that you can keep traversing the list without ever reaching a null value. Means in the, of course, here the figure is about double linked list. By mistakenly, I placed the same thing. Actually, circular linked list will contains the value of the previous first address. I mean, this is double linked list figure actually. So the reference will always contains first node's address, so that it will be in a circular form. Okay, in such a way, circle linked list will work. And In the next class, we will discuss about the trees. In the next class, we will discuss about the trees. And here, because of this system is not supporting, I'm not able to take. Hmm.